Let's use our test to test the following equations for symmetry with respect to the axes and the origin, and see if we can reduce the amount of work involved in graphing these equations. So let's run all of the tests together. We can make our own table here. And we're going to test for the different types of symmetries. So we're going to test first for symmetry with respect to the x-axis. And our action is to replace y by negative y in the equation. So what happens when I replace y by negative y here, for x equals the absolute value of y, I get x equals the absolute value of negative y. Now this is actually the same equation, because the absolute value of negative y is the same as the absolute value of y. So that's the same. So I have symmetry with respect to the x-axis for the graph of this equation. What about y equals the square root of 9 minus x squared? When I replace y by negative y, I get negative y equals the square root of 9 minus x squared. And I get y equals negative the square root of 9 minus x squared. That's not the same equation. Here I have y equals some positive number, and here I have y equals some negative number for any given x, so they could only be equal when y equals 0. And you can easily check that there are some points where y is not equal to 0 in this equation. For example, when x is 2, then I get the square root of something positive. So this is not the same. So I cannot conclude symmetry with respect to the x-axis here. What about this equation? When I replace y by negative y, I get minus 8y equals x cubed. Again, I have the same thing. This equation is the same as saying 8y equals negative x cubed. And we can easily find a couple of examples for a given x value, say x equals 2, then y would equal 1 here, and y would equal negative 1 here. So they're not the same equation, and so we cannot conclude symmetry with respect to the x-axis here. What about symmetry with respect to the y-axis? What does our test say? We should replace x by negative x in the equation and see if we can figure out if we have the same equation or not. If it's obvious that we have the same equation, then it must have this symmetry. Sometimes it's difficult to see whether you have the same equation or not. It's not always as easy as getting y equals the negative of the previous equation. And if you can't obviously see that it's the same equation, then you can't conclude symmetry. What happens if I replace x by negative x in this first equation? I get negative x equals the absolute value of y, x equals negative the absolute value of y. Now this is not the same equation. This is not the same as saying that x equals the absolute value of negative y. This means x is the negative quantity of what it is in the previous equation. So for the same reasons as I gave here, this is not the same equation, and I cannot conclude symmetry with respect to the y-axis here. Let me replace x by negative x in this equation, y equals the square root of 9 minus x squared. I get y equals the square root of 9 minus negative x squared. And this is actually exactly the same equation, because negative x squared is the same as x squared, so that's the same. So I can conclude symmetry with respect to the y-axis here. What about symmetry with respect to the origin? What about symmetry with respect to the y-axis for this equation? Let me replace x by negative x. I get 8y equals negative x cubed. Again, I get 8y equals negative x cubed, and this is not the same, for exactly the same reasons as I gave up here. And so I cannot conclude symmetry with respect to the y-axis there. Symmetry with respect to the origin. My test is going to be to replace both x by negative x and replace y by negative y. And if I obviously get the same equation, then I can conclude symmetry with respect to the origin. Well, let's try it for this first equation, x equals the absolute value of y. If you recall, when we drew this graph, this test should come up negative here. Let's try it. We replace x by negative x, and I get negative x. I replace y by negative y, and I get the absolute value of negative y on the right. So once again, that's equal to y itself, or the absolute value of y itself. And once again, I end up with x equals negative the absolute value of y. And these are not the same equation, because here we have x equals some positive quantity, and here we have x is a negative quantity. So they're not the same. And so I cannot conclude symmetry with respect to the origin here. How about y equals the square root of 9 minus x squared? Well, I replace x by negative x and y by negative y. And I get negative y equals the square root of 9 minus negative x squared. That's negative y equals the square root of 9 minus x squared, or y equals negative the square root of 9 minus x squared. So as in the above case, this is not the same. I cannot conclude symmetry with respect to the origin. How about this one? 8 times negative y equals negative x cubed is what I get when I replace x by negative x and y by negative y in the equation. This says negative 8y equals negative x cubed, because negative 1 cubed is negative 1. And now I can cancel the negatives, and I actually do get symmetry with respect to the origin in this case. And you can see it's a setup. This one has symmetry with respect to the origin and no other symmetry. This one has symmetry with respect to the y-axis and no other. And this one has symmetry with respect to the x-axis and no other symmetry of the three mentioned here. How about the graphs? Well, x equals the absolute value of y. We've already drawn this graph. We've taken a few points, but we've concluded above, if we were to redraw the graph, that this has symmetry with respect to the x-axis. So how can I use that in graphing? Well, I only need the top half of the graph. So I only need draw the graph for y greater than 0, greater than or equal to 0, let's say. Because it has symmetry with respect to the x-axis, if I draw the top half of the graph, I can just fold it over the x-axis to get its reflection and the second half of the graph. Let's take some values of y, 0, 1, 2, and the corresponding value of x is 0, 1, and 2. So my points here, I have 3 points in the graph. I'm assuming it continues that way along this diagonal, or this diagonal ray from the origin on to infinity and beyond. And now that's what the top half of the graph looks like, and because of the symmetry, I can just reflect this in the x-axis to get the bottom half of the graph. So it gives me a sketch of the graph of x equals the absolute value of y, and it reduced the amount of work by half in this case. What about y equals the square root of 9 minus x squared? Well, I've concluded that this has symmetry with respect to the y-axis, so I need only the right half of the graph. What is the right half? It's the points where x is greater than or equal to 0. And then once I have this, because of the symmetry, I can just fold it over the y-axis and get the other half of the graph. Now I need to think about this equation a little bit before I start graphing. Y is going to be a positive number here always, and it's not going to exist if x is bigger than 3. So the domain of this function, or this equation, the only x values which make sense, which are greater than or equal to 0, are those between 0 and 3. So I'm going to check out the values for x equal to 0, 1, 2, and 3. And here I have y equals the square root of 9 minus x squared. And this is 3. Y equals the square root of 9 minus 0. Here I have y equals the square root of 9 minus 1, so it's the square root of 8. It's 2 times the square root of 2. And here I have the square root of 9 minus 4, which is the square root of 5, which is just a little bit bigger than 2. When x equals 3, I get the square root of 0, which is 0. So I can graph these points. So I'm talking about x equal to 0, 1, 2, and 3. And I see that my range of y values is running between 0 and 3 here. I have the point 3 zeros on the graph. The point 0, 3 is on the graph. The point 1, 2 times the square root of 2. That's up here a bit. About here, 2, and the y value is the square root of 5, and that's about here, and I join those dots and I get this thing that looks like a quarter circle. And that's the right half of the graph, and then I can reflect that in the y-axis to get the image, its reflection, and I get the other half of the graph. Now this looks like the upper half of a circle, and that's exactly what it is. Notice that if I square this equation, I get y squared equals 9 minus x squared, are x squared plus y squared equals 9. And so this is the equation of a circle, but by squaring, we're getting more points here. So the graph of this equation includes the lower half of the circle. We've lost some information here by squaring both sides. Here y is only allowed to take on the positive values in this circle. So we really just have the upper half of the circle. So there are some y values which satisfy this equation, which do not satisfy this equation, namely the negative y values on the graph of the circle. The other half of the circle is described by the equation y equals negative the square root of 9 minus x squared. Let's draw our final graph. This is the graph of 8y equals x cubed. And I know that this has symmetry in the origin, so I just need to draw either the upper half of the graph, or the right half of the graph, or the left half of the graph, and rotate that by 180 degrees, or push it through the origin with the symmetry to get the other half. Well, this is relatively easy to draw because it's y equals x cubed over 8. And I'm going to draw the half of the graph which corresponds to the right-hand side of the plane, which corresponds to x greater than or equal to 0. And then once I've done that, I'll use the symmetry to get the other half of the graph. So when x is 0, 1, 2, 3, I get when x is 0, y is 0. When x is 1, y is 1 over 8. When x is 2, y is 8 over 8. And when x is 3, y is 27 over 8. So one half of this graph looks like this. When x is 0, y is 0, so 0.00 is on the graph. 1 over 8, 2, 1, and then we see a big jump. 3, 27 over 8, which is 3 and 3 over 8, so it's up here somewhere. So we see this graph that picks up speed as we go to the right, and we assume it continues in that vein. And then the rest of the graph, or the other half of the graph, is the reflection of this through the origin. So if I take any point here, push it through the origin, I should get the corresponding point is on the graph. So our graph looks like this.